Hey everyone, so I'm Gunveil, and I will be speaking today about, well, the recent drama in InfoSec and open source communities, I guess, about the XZ and liblzma backdoor, which I guess you would have to be living under the rock if you don't know what this drama is about. Now, I'm going to focus only on a small part of it, which I actually analyzed, which is um, the bash obfuscation part of how the backdoor was actually injected into the whole compilation process. So a little bit about myself. I've been working in security for, I don't know, like 17 years. I've been programming forever. I've written a couple of books or co-written a couple of books on programming and security. I'm also the creator of a Zine called PageDAO. So if you like hacking Zines and programming Zines, please check us out. We are always looking for authors, and every page is just every article is just one page, so it's pretty easy to write it. All the other information, I guess, you can find on the internet. That's not really super relevant to today's topic because we'll be focusing on some bash. So I guess, like, if you want to read more about the whole story, more about the whole drama, then there are other better resources than this talk on the internet. What I would advise you to do is basically check out the original first post on the open source security mailing list. This is what started and made everything going, basically created the whole investigation for us. And then there are like a couple of really good posts from really smart people, basically until here, until like these two is something I would recommend, as well as El Cantus, the two links at the bottom. And if you're more into the actual how does this backdoor work in, the technical nits and grits, basically, and you're into reverse engineering and so on, then I would absolutely recommend these two resources, being Blasty on Twitter and as well as this repository where the XZ bot has been posted, which is, I guess, like these two resources are currently what's the best out there. This being said, the actual backdoor is still being reverse engineered. We, as the community, we don't know everything about it yet. It's pretty heavily obfuscated. But again, that's not really the topic of today. So let's switch to the actual bash part and the actual part which oh, wait. Everything I'm talking about today, if you prefer a written form and you prefer to look at the code, just go to my blog, and the newest post is about basically this. So the heroes or anti-heroes of today's talk are going to be free files. Free files, which are like, from the bash perspective, important here, are the build to host.m4, which is the initial script, stage 0, how I call it, of the actual injection process. And then there are two tests. These tests you can file if you download the liblzma, the source code of the, or rather the tar of the source code, the malicious tar of the source code with the backdoor. Then if you go to tests and files, you'll see two other files there, and that would be the bad free corrupted, as well as good large compressed LZMA. Now, battery corrupted basically is stage 1. If you would open this file, which we could actually do, so let's view this file in a little bit of hexadecimal. Well, it kind of looks like it has this header, like 7-zip, but you cannot see here too much apart from world and hello here. So some hello world things, everything else is like yeah, there's nothing there. And if you try to unpack it, it will actually not work because it is, as the name implies, corrupting. The other one is a little bit bigger. It's 35 kilobytes. It's also, if you decompress it, it decompresses correctly, but what you decompress to is obfuscated, so you also cannot like see anything there. Okay, so let's look at the initial stage, what is basically happening. And for that, I'm going to open this file. There we go. The font is a little bit too big, but that's fine. So this is the M4 file, which is part of the, I believe, AutoConf and other tools which are basically in the long chain of building the this library. it's like it's run at the initial stage, basically, before the configure file is generated, before you start compiling things. Now, the interesting part here is if we jump down to the bottom, is basically this line here. And this line, kinda, we can say that it defines a function. That's not fully true in technical sense, but that's how I'm going to call it. So let's say that this creates a function which is called glPathMap. And what this function does, I'll explain in a moment. But let's see, where is it called? And it's called in this actual line. So what's happening here is this is, you know, an ongoing process of the whole building of the library, and then we suddenly get into this line, and this environment variable is set to the file which I just showed you, the bad corrupted file, the bad file. So we first run a sed script on it, and this script is kind of funny because if you run this file, we can run it. Just running these commands without running the eval is pretty safe. So remember that eval is evil, so don't run eval, but everything else we can basically run if we are careful, and it should be fine. So let's run the sed, and I need to modify it a little bit. Okay, this should be fine. And what I'm going to run it on is this bad file. And what it does, it doesn't do honestly that much. Is like what it does is just like adds a new line at the end of a file. And I'm not even sure if that new line is needed there, but I don't know. Maybe there are some other intention there. But yeah, this is basically what we get there. So let's send it to a file called stage 0. And then what we get is eval of that function. So it's basically running that function. So if we again look at that function, we see that what it's actually calling, it's calling this translate function, or rather translate command. What the translate command does is it takes an initial, let's maybe actually write this down. So it's going to happen here is translates a certain map of characters into another map of characters. And in this case, we have 4 characters as the initial set. That would be a tab, then a space. This is a white space. I'm just going to write white space. Then we have an escaped dash, but this is just a dash. The escape there needs to be due to some TR, the way TR works, but it's just a normal dash. And then at the end, we have an underscore. And these 4 characters are translated, changed into, well, these output characters. So in this case, we have a space at the beginning. So here's the white space. Then we have the tab. So white space, a tab is changed into a white space is changed into a tab. And here, like really similar, we have a dash being changed to underline, and the underline being changed to dash. So this doesn't do too much. It doesn't do that much, but well, this file is called corrupted, and this is uncorrupting the file. This is basically what it does. By doing this simple transformation, we uncorrupt the file, and then we will actually be able to unpack it. So let's do that. Let's do this. We have to cut the bad file into this command, and then we can save it to stage 0. Let's call it step 2.bin, for example. And now we have an uncorrupted file. So this uncorrupted file just like changed these, did this transformation, and we can check what's happening later down the line with it. So then we basically run this, which is xz. This under this variable we get xz. And we do -d, which -d here just decompresses it. So basically what it does, it decompresses the file. So here, sorry, I did do a simple mistake here because I was supposed to grab the previous step's output. So let's fix it now. And then we can cut the step 2, and we can send this to xz-d. As you can see, it sends errors to dev null. There is like one minor error. I'm not going to do that. And we are going to send it to, actually what this is going to be, is going to be state 1. There's unexpected end of input. That's okay. The file was still created. The file was still decompressed. And if we open this file, what we find is we find actually a bash script. So this is what I called stage one of the whole bash part unpacking process. At the beginning, what you see, it like basically checks really heavily if this is a Linux and not something else. This was, I believe this part was missing in the previous version. The files which I'm operating on during this demo are basically from the 5.6.1 version, but also backdoor was the version 5.6.0. There are some minor differences between them, and this part was basically added as well. So I guess like the initial backdoor was causing issues when it was compiled on, I don't know, other platforms, so this was added. Okay, and then we get to this part, which is kinda funny. But before we analyze what's going on here, I'm going to direct your attention to the semicolon, which basically means that we are, well, these are just like two commands. The first command is, again, let me just say that this is defining a function. Again, that's not technically correct. This is not how you define a function in Bash, but looking how it's used, it's basically a function. So this function is called I, and what it does, it actually is really simple, even though it looks a little bit like what's going on here, but it's actually pretty simple. And then what we get is we get a chain of commands where one command's output is the next command's input. So we have the first in the chain is just like decompress the good file. See, this is where the good file, which I showed you at the beginning, comes in. And then the output of this is being sent to basically this function. So we run this function, and the output of whatever this function does is being sent with, let's make it like this, is being sent to tail-c with some number. What this does is it basically just grabs the end part of the file. So, or rather of the data. There will be some data. Assume that this evil I actually outputs data, and what tail will do is we'll just grab the end of the data. Everything else will be, everything at the beginning will be disregarded until we reach kind of 32 kilobytes. Then we have another translate, and what this translate is doing, this is basically, again, it works the same way as what I described here, just we have like more characters on left and right side, and these characters are defined by their octal codes, like ASCII codes, but not in decimal, not in hexa, but in octal for whatever reason. Well, the reason being that this is what TR actually supports. So we have ranges, which means like if there's a dash, this means like take codes from 114 octal to 321 octal, and then another range is defined and another range. So instead of like writing the 114, 115, and so on, we can just write a given range and then another range and then another. And these ranges, if you would actually like write down these ranges, you get 256 different byte values in the input. So this is the input part of the translation map. The output part is just mapping between 0 and 255 as the byte values. So without going into the actual maps, what this does is it's a simple substitution cipher, which means it takes a given byte value and translates it into a different byte value. This is why I told you that again, if you would decompress good large compressed, then we wouldn't actually see too much there because it's, well, it's obfuscated and encrypted in this case. This isn't the greatest encryption, but it is encryption. And here it doesn't have to be great. It's just supposed to obfuscate, like, you know, like a simple analysis. And once this is obfuscated, deobfuscated, rather deciphered, it's being sent, the output is being sent yet again to basically decompression. So we are decompressing at the beginning, then fixing stuff, and then decompressing what we get at the end as well. And then we are sending this to bin bash to get executed, which kind of already tells us that, hey, what we get as the output of this command is basically going to be another bash script. So, okay, let's deal with this function because it looks scary. But what it actually does is it's made up of two elements. One element looks like this with brackets, with parentheses, and its output is being redirected to devdul. And the other element is basically the same thing, just a different value, 2 kilobytes here, 1 kilobyte here, without the dev null. So what we get is basically, this means skip 1 kilobyte of data. This means output 2 kilobytes of data, skip 1 kilobyte. Next thing is going to be output 2 kilobytes, skip 1 kilobyte, output 2 kilobytes, and so on and so forth. If you'd actually go to my blog, you will find this here, which is, this is how the file looks like if we would see it as basically as pixels. We see these like areas where is like there's no effective data, there's just like one letter repeating like A. And then there's some like this like high noisy data. This is the actual compressed data. So what happens here, what this function I does is it removes the empty spaces. This is all it does. It removes the empty spaces, so we get like all this noisy data we can decompress later on. Okay, so yeah, this is what it does, like literally the only thing. And knowing that, we can actually start to walk through it, which means we can first decompress the good large file. This is fine. You can just decompress it to stage 1, step 1. Let's call it the bin. Only it says that it's not here because it's in the, I already copied this file. We don't have to go there. Then we are going to run this function. So I'm just going to basically define this function. This is fine, but I'm going to call it a little bit different. Let's go like this, for example. Okay, and now I need to use evil, but that's fine. I actually know what's there. So I grab the step from the previous step, which I already did, and now I'm calling eval and grabbing this the ob script, and then I'm going to output it to stage 1, step 2 dot bin. Now, if we quickly take a look at step 1, so this is step 1 in a hex editor. You can see the empty area with just repeating letter A. And then if we scroll, there is this high entropy compressed data. Then there is like B, basically that's another empty space and so on. And if we look at the output, we get only this high entropy data, which after deciphering, we'll be able to decompress. So, well, first of all, what we got, the data we got actually has like 2 parts. The first part is the actual backdoor, which is going to be injected into the compilation process. We'll get to it in the next stage, in stage 2. But the stage 2 bash script is actually just at the end of this data. So this data is, again, like 2 parts, which isn't really visible in the entropy, but it's like that. Like this part here on the left until like this point, let's say, is basically the backdoor and the binary backdoor, and the other thing is the compressed and obfuscated bash script. So let's focus on that. Let's just grab the end of that file. We can do stage 1, step 2. We can cut it into cutting off basically the tail of it and just focusing on that tail. Step 3, the bin, and then we can decipher it. So I'm just going to do the same. And then we decipher it, stage 1, step 4, the bin. Okay, and then after this is being done, we can just basically decompress it. You can see there is like no headers. The -f raw means that the format is raw. This is a pretty advanced option, I guess, because you have to define in the comments what's actually going on there. So what we are going to do is we are going to cut this, decompress it into, and this is already being decompressed into stage 2. The bin is not actually bin, it's actually a bash script, as we will see in a second. So this is the second stage, counting from 0. There's a lot of things going on in this stage, which is not really important for the obfuscation part, which I'm focusing on. Russ Cox actually has described really well what is going on in the script. So the links were before, and I guess like we can share the links afterwards as well. So I'm going to skip this part. I'm going to also skip this part, which is described on my blog. This is because this isn't actually now doing anything. This was like a future-proofing extension interface for this backdoor injection process. It's pretty interesting, but currently it doesn't do anything. It's like a plugin system basically for this backdooring, which is pretty weird, honestly, but pretty amazing at the same time. If we scroll down, the really interesting part is basically getting to where is the part which I'm looking for? Okay, here, there we go. So the part of extracting the actual binary backdoor is the interesting part, and it's happening on line 209. First of all, we are repeating the steps we did previously. So what we are repeating is we are repeating this step here, where we did the decompression. We already have this file, so I'm not going to do anything. The next file is calling this I function again. This is the same function, because the script is running in the same context, bash context, which means it can use actually the previous functions. So what we can do here now, we can also omit it because we already have this file. This file was run here, and we have the file created at this point, so we can just reuse that file. And then we are using sed to, again, kinda, so this is actually interesting. It actually takes every byte of the file and it adds a new line, with the exception of a single new line. If the byte has the value of a new line, then it's actually not going to do anything. But for every other byte, it just adds a new line afterwards. And this is because it later on runs this awk script, which we'll focus on in a moment. So let me do first this. I'm going to grab this stage1 step2.bin file, and I'm going to run it through this. And this is stage2 step1.bin. And I actually have too many of these. There we go. Okay, so now let's focus on this awk file. I'm actually going to run it first before we do anything else, because I want to make it a little bit more readable, and that will kind of break it. So stage2 step2.bin. Okay, and let's go quickly through the script. What does it do? So AWK is like, if you know Perl programming language, AWK is like the simpler version of it. It was created to operate and do operations on text files. It's pretty cool if you want some like a little bit more control than tail and head gives you. Then AWK is pretty amazing for that. So what I'm going to do is I'm going to quickly add a couple of new lines here, which makes this a little bit more readable, but we are not going to read it that much for a very simple reason, because this really isn't anything, how to say it, it's not something which is new. It's actually an implementation of another encryption algorithm, and that algorithm is RC4. So a couple of more enters, and we can plainly see it. Okay. So the way it works is that everything after begin in this begin block will happen at the like initialization stage, and then everything which is without begin in this other block, this will happen for every line. And as we remember from the previous step, in every line we have just one byte. We just have a byte, nothing more. Now, if we go to Wikipedia for RC4, we will see the following formulas, basically. Is at the beginning and the initialization step, just like set one array from 0 to 255. And if we scroll here, we can see that this is actually what's going on here in this part. The part below that is creating the cipher key, because if we have like a cipher, an encryption algorithm, well, we need to also have a key, and the key here is hard-coded. It's like doesn't come from anywhere else. It's just hard-coded, literally in this line. And then everything else is basically standard, like it's skipping first 8 kilobytes of the cipher, or rather the PRNG stream generated by RC4. This isn't really a crypto talk, so I'm not going to go too deep into this. Let's just say that this is pretty standard initialization for RC4. And this is basically decryption with a minor change. Usually you would, I believe here, have an XOR operation. Instead, AWK, I'm not sure if it really supports XOR or not, but for whatever reason, plus was used, which is fine. That's absolutely fine. And yeah, so You don't even have to analyze it as long as you recognize that this is RC4 algorithm. So we already have this unciphered, deciphered, or decrypted rather. And the last step, the really last step, is to just decompress it, decompress the stream, and then just like grab the first part of the stream. But we can actually skip that. So I'm just going to decompress it, step 2.bin, into stage 2, step 3.bin. And now if we look at that step, we'll see that this is an ELF file. And this is actually, if we do a file on it, stage 2, step 3, we find out that this is, like a non-relocatable, blah, 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 but this is actually an object file. An object file is what you get if you compile, if you're compiling a C code, you actually get assembly, and that assembly gets compiled into an object file. And then a linker comes and it takes a lot of object files and it creates one executable or one library, like dynamic short library from that. So this is what we get, and this is the backdoor, which later on, and in the script actually in stage 2, is being interweaved into the whole compilation process. But that's basically as far as we go today. I hope this topic was interesting for you. If you are interested in that topic, then again, ideally, please go to these websites, as they have way more information on the whole process. And if you're interested in reverse engineering, the binary backdoor is super interesting, but it's also super obfuscated as far as these things go. So yeah, like just follow Blasty's analysis, for example, or read everything else which was already written about the topic. It's pretty cool. Yeah, the whole thing is pretty big, and and it's pretty unfortunate that it happens, but it also is kind of another wake-up call for us in the security and open source community to think how we approach things. And that's it from me. So thank you very much for listening. And if you have any questions, I believe there will be an occasion to ask them in a few moments.